Okay, and so you'll see this integral as signed area. That's the first one, so you click on that. These are problems. You have limited attempts. Okay, notice you have limited attempts. And a big thing I want to show you about these problems is you can enter expressions for your answers. There's some people that just watch for people that haven't gotten one. You can enter expressions for your answers. You don't have to have a handheld calculator next to you punching while you're doing the problems and then enter a decimal approximation. So you can put in things like e cubed minus 2 divided by pi squared plus, square root of 107. 108, that's what I meant, okay? So you can let it be the calculator for you, and there's some advantages to this, okay? There's some advantages to this. So you put that in there. Preview answer. This is unlimited. You get unlimited preview answers. So when you submit, that takes away an attempt. But preview answer, you get unlimited. And so one thing the preview answer does is it tells you if there's just an error in what you've done. So before you submit, so you would get it wrong if you submit, but this will tell you without wasting an attempt. So, I got a missing close parentheses. I didn't even mean to put that there at all. Okay? So get rid of that. And then preview again. And then I look at, so now it's giving you a nice image of what you put in. I said, oh no, that's not anything what I wanted. I wanted e cubed minus 2 all over pi squared plus square root of 108. So I did need parentheses here around this. So I can change this. Notice I haven't wasted any attempts yet. Preview again. Okay, is that what? No, that's not what I wanted. I want pi squared plus square root of 108 all in the denominator. That's what I meant to write. So what do I have to do? I need parentheses here too. And so then I do this and preview. Oh man, I screwed up again. I got parentheses in the wrong place. Notice I haven't used one attempt yet. And I'm getting all this very useful information. I haven't touched my handheld calculator once. That's where I want the close parenthesis. Finally, okay, this is what I wanted. I wanted e cubed minus 2 over pi squared plus square root of 108. Okay? And then, so that's an exact answer. You never have to worry. Here's the other advantage of this. You never have to worry about, did I include enough decimal places or not? Because that expression is an exact answer. And then it gives you a decimal approximation there as what you're entering by entering that expression. Okay? So you don't need a handheld calculator. Let WebWork be your calculator. Enter expressions. Use answer preview. It's really, really helpful. Okay? Any questions on that? And then once you see a green bar, so this will now I'm ready to submit, right? Ready to submit. And then I get the feedback, okay? Of course, that was wrong. When you see green, there's nothing else you have to do. You got credit. It's all saved in the system. You don't have to do a, like final submit or email me and tell me, what you got right. It's all saved once you get the green, okay? Questions on WebWork? Yes, please. No. So if you get it right on the last attempt, you get full credit. Okay. So, and then the reason for multiple attempts is like kind of for this, which you have answer preview for also, is like typos and thinking through it. So it's not for guessing, right? It's not for guessing. It's for just technology errors, right? And your own just errors. Okay. Plus, 7 gives you some room to figure out what's going wrong, right? Figure out what's going wrong. So stop and think about it. Don't just guess. Any other questions about WebWork? Yes, please.
For the unanswered questions, if you submit like the first one,
yeah,
say incorrect, does that count as a?
This is one. You get this is that would be one attempt for all of them. There's no separate attempts for separate parts. Once you do an attempt, you're attempting all. So yeah. So this was not wise of me. I should have tried all of them before I hit submit. Okay. And then some problems they'll give you partial feedback. They'll tell you which ones are green and red. But then problems sometimes you have to get them all right to get the credit, and they'll just tell you at least one of them is incorrect. So you got to go back and figure out which one. Last question.
If you get like the first 2 right, and then like on your second attempt, do you have to get all 4 right, or like
Just,
The right answer is like say.
just if you leave them, then they'll stay. Yeah, don't change them. If they're right, don't change them. Okay, that's that. So then there's a follow-up in the written homework. There's a written homework that's based on the web work integrals, and so all problems in the web work are of the form of a definite integral. So in your web work, there's no integral functions like we've been really working on. So they're all definite integrals like this. So I want to do a little exercise of thinking and writing, where you're going to interpret these as they are related to integral functions. Okay, accumulation functions. Okay, so how could we relate this to what would this have to do with an accumulation function? What would this have to do with an accumulation function? What's one thing about this? What about f of x? The rate of change function, right? This is the rate of change. You know how fast something is changing at every moment, okay? All right, what about the 1? The x coordinate where we're going to start accumulating from, right? We're going to start accumulating net change from 1, okay? What about the 2.4? And what does it have to do with the function? So if I'm thinking of this as an accumulation function, what does the 2.4 have to do with a function? What's that? Yeah, that's true, but what does it have to do with, if we think of this as an accumulation function, what does the 2.4 have to do with the function? How does it relate to the function? Independent variable, okay? Right, so it's a particular value of the independent variable, right? With a function, we let x just vary. The right-hand side is just increasing. So then we can use the function and we can say, okay, I want to know how much accumulation I have at 2.4. So it's like we're plugging in 2.4 into the function, right? Because that's our independent variable there, x. All right, so here's a possible, so I want you to do it in your own words. You're not just rewriting this. In your own words when you do this part of the homework. So here's an example. This is the function value capital F of 2.4, where capital F of x is integral from 1 to x, f of t dt. Capital F is the net accumulation of signed area for the graphed function little f. Capital F 2.4 is therefore the net accumulation of signed area of f as x increases from 1 to 2.4. So that's an A++ explanation. It's breaking that thing down as one particular value of an accumulation function, explaining how that works. You're going to do the same thing several times, 4 or 5 times. Again, I don't want you to just take the sentence and fill in the blanks. I want you to, don't look at this, think about it and see if you can write it in your own words, okay? So that's part of the follow-up to the web work, a little written exercise to make sure we're seeing all these integrals as still relating to accumulation function. Any questions? Okay, very good. So let's jump to the sheet that we handed out. So you're gonna work on, this is review. You're gonna work on everything, these 2 parts. So the first 2 parts that have illustrations, right cylinders, we'll talk about that later. So not right cylinders, but this is review. And it's gonna transition into our next topic, which is accumulation of volume. Okay, so that we talked about accumulation of area. We talked about signed area, right? So the integrals give signed area. So this is a review of that. I'll just give you a hint. This is a phrase. This is a phrase. The first blank is a phrase, and the second blank is a number. Okay? First blank is a written phrase. Second blank is a number. Go. I'm going to start attendance. Everyone's making progress, or you're getting help. Okay? You're making progress, or you're getting help. Everyone have a sheet. Everyone has a sheet.
Oh, oops, sport. I assumed it was the.
Yeah, just to your TA. It's fine. Yeah, these guys are in class late. Right. Yes, right.
I like that.
Thanks for reminding me.
Which means for every head for x,
I'm sorry? Yep. Mm-hmm. Yeah.
There's 3 units squared. Or just 3 units squared, actually, because you said, now that I'm thinking about it, you said why.
Eric. Is Eric here? Sebastian. Kyle. Nico. Nico here? Anna. Clayne. Grant. Grant. Nick. Kane. Lauren. Is Lauren here? Maya. Jamie. Tresta. Catherine. C. Catherine. Cameron. Cameron here? Lindsay. Dinu is here. John C. John. Susanna. Susanna DeFusco. Nam. Steve. Victoria. Judith. Anthony. Justin. Zoe. Everett. Saul. Daniel. Foreman. Johan. Chase. Tanya. Oz. Nick. McKay. James. James who? All right, where's... Did you get this first one? The rectangle area grows at? Constant rate. What do you think? Agree? Let's go blue. A constant rate of 4. And if you said constant rate of change, that's good too. So the rectangle's area grows at a constant rate, or a constant rate of change of 4 with respect to its length. So length being what? X or Y coordinate? Yeah, so they're calling this the length. That's our X. Which means that what? So let's see, have we learned something new in this class? What does a constant rate of change of 4 mean? Let's spin the wheel. James, what does a constant rate of change of 4 mean? What does it mean? What's that? Continually change by 4 in any given interval. Okay, how about, where's Ray? Lau. Is Ray here? Allison, Mulham.
So the area is going to change at constant rate of 4 units squared per unit.
And what is, right, and what does that mean? What does it mean, a constant rate of change of 4 area squared units per unit? Yeah?
The rate of change of area is
Right, and what does that mean? So we've got it. It's the rate of change. 4 is the rate of change of area with respect to length. What does that mean? That's all.
For every change in length, the change in area is that change in length times 4.
You got it, right? Do you remember this? What's the theme? dy equals mdx. And so what's our y in this case? What kind of quantity is y? Area. Okay, our rate of change is 4 and dx. What does the rate of change of 4 mean? It means you can change x by any amount you want, and then you know what the change in area is. What's the change in area? 4 times whatever change in x you picked. Does it at least sound familiar of me up here ranting and raving? Okay, so one of these times is going to stick, and when you say, what's the meaning of a constant rate of change? You're going to oh yeah, I know. Given a change in your independent variable, the change in the dependent quantity, which in this case is area, is 4 times the change in the independent that you picked. That's what a constant rate of 4 means. Okay, so I'm not going to write that out. So that's what you would hear. Given any change in length, the change in area is 4 times the change in length. dA equals 4 dx. Okay, next one. All right, let's see. Alan, where's Alan Roth? Alan, tell me about this next one. The region's area grows at, what did you put for this?
Changing rate.
He wants a changing rate. What do you think? Yep, grows at a changing rate or a changing rate of change. Of what? What is that changing rate? What's the value of the changing rate? Or how could we symbolize it? Okay, x is, what is x? X is our current value of the independent variable, is x. So then for that value of x, what's the rate of change? How could you say what the rate of change is?
F of x.
He wants f of x. F of x. So the changing rate is f of x. It's according to x, right? And it's the value of the function. That's what we worked on last time. We said, or the last 2 days. So given any value of x, how much is the rate of change changing? Sorry, no. What is the rate of change of area? What is the rate of change of area? Well, it's whatever that kind of, if this is my current x right here, how much additional area do I get? Well, I'm going to get according to that value of the function value, right? Think if I increased x a little bit, how much more area would I get? Well, that much. And that's the function value, right? That's how tall the function is. All right, which means that what? Somebody knew. What does it mean that the changing rate of change is f of x? Yeah, Nick.
For any change in length, the corresponding change in area is f of x times the rate of change in length.
All right, so let me write that out. For any change in x, the corresponding change in area is f of x times that change in length. Or, yeah, that change in x. What do we think? Almost. There's a subtlety here that's something different about this. So it's not quite correct. He's got this, the spirit of it is right. We got the spirit of rate of change, but there's something going on here that we have to point out. Yes, sir.
3 times dx.
Yeah, that's change in x. That's what dx is. Yep, change in x, dx, same thing. What's going on here?
Isn't it the value of the function at, like, where f of x is?
Yeah, that's what f of x is. Okay, yeah, the area, the rate, the corresponding change in area is, you're saying, the value of the function. Yep, that f of x is the same as the value of the function. All right, Catherine.
Oh, but it's like that, like the most recent change in x, like that.
Okay.
The most current.
Yeah, so when you say f of x, you're talking about at the current value of x, because that's what this means. So here's the issue. Is it for any change in x? How about, can I do a change of x of 1? Will that work? What if I start right here at the where it stopped, and make my change of x 1? Is this going to give us the change in area if I multiply this f of x? If I take this f of x right here and multiply it by this dx, why not? Is it going to be too high or too low? It's going to be way too low, right? Yeah, so instead of any change in x, what kind of change in x will this work for? Only small, because the rate of change is changing, and now it only works for small change in x. So we can leave any, but then we just need to add for any what? Small change in x. If it's big, it won't be an accurate, you won't get an accurate change in area. But if you have a small enough change in x, then we can say, oh, it's virtually, for a small change in x, we can just suppose it's virtually constant right there, right? So we just say it's virtually constant function right there, and we can do dA equals f of x dx. But big changes will work for the constant rate, right? It doesn't matter how big your change is; it'll work perfectly. But as soon as that rate is changing, this is going to only work for a small change in x. Okay, any questions on that? Okay, so let's talk about right cylinders. So this is now we're going to transition from area into accumulating volume. And what we're going to do to accumulate volume, this is just a broad overview, is we're going to use a function to create an empty shell. An empty shell, and then we're going to fill up the shell. We're going to accumulate elements inside the shell to fill it up, and so then we'll be keeping track by the function of the accumulation of volume in the shell. Okay, so what are we going to fill up these shells with? So we're going to fill up these shells with a certain kind of right cylinder. So let's talk about right cylinders. So a right cylinder is just in general, you take any shape you want. Okay, take any region you want, and then you're going to just extend that perpendicular to the plane of that region and keep that region the same. So I'm going to see if I can redraw this here. Not bad. Okay. Not great. That's not good. Let's try again. Yeah, better. Okay. So if I take that region in a plane and then perpendicular to that plane, I'm just going to just extend that region. I get what's called a right cylinder. Okay, because you're moving it through a right angle like this, right angle to the plane of your original region. And so then anytime I slice this thing like this, I'm going to get the same region. That's what a right cylinder is. So if I slice it in the middle, all right, if I slice it in the middle, I'm going to get that same thing again, that peanut shape. So when you think of cylinder, you might think of like a tin can or a soda can, right? Doesn't have to be, that's a circular right cylinder. It can be any shape. You can start with any shape. So I can start with any shape like this with a hole in it. And then I take that and I'm going to lift it up perpendicular to that thing. With the hole also. I try not to, this is terrible. This is the worst thing I've drawn all day. It's also the second thing I've drawn all day. Okay, so, but you get the idea. So I've got this shape. So every slice I take of this thing, I'm going to get that same base shape, same exact base shape. Okay, so you draw three, any three that you want. Make them simple. Don't try to make them complicated like mine's. Make your base shape simple and do one of them with some kind of hole in it. Okay, so so I tried to draw a real pretty one to make it up to you. How'd I do? All right, so that's a right cylinder, right? It's a right cylinder. I started with a triangular region. I just let that region extend perpendicular to the plane of the region, so it just keeps repeating itself, like a deck of cards, right? Like a deck of cards. You get the same thing every time you go up. Same cross, what we call cross section. That's a right cylinder. Okay, so there's a specific type of right cylinder that we're going to use to fill. I talked about creating an empty shell. We're going to fill it with a specific type of right cylinder to make our volume accumulation functions. Okay, so let me show you what those are. Those look like. Okay, do you see that those are right cylinders? Okay, so those are right cylinders. Okay, so they're circular and they have a hole in them. Okay, they're circular and they have a hole in them. Okay, so these are the types of right cylinders that we're going to use to fill up empty shells, and then we're going to track the accumulation of volume of those cylinders as they fill up the empty shell. Okay, now there's two ways that this accumulation can happen on a cylinder like this. So watch. So for these cylinders, we can have cylinders of what? Changing height, and we can have cylinders of changing radius. So it's the same type of cylinder, but one is we fill up the shell by having cylinders of changing height, and the other type we fill up the cylinder with we fill up the shell with cylinders of changing radius, like on the right. Do you see the difference? See that? But we're going to fill up empty shells with cylinders, either like the ones that are like this with changing height, or this with changing radius. So we're going to work on changing height first. So you can flip over your page. Move this down here. Just gonna let this start running. So you're imagining this is this. We're going to talk about this situation first. So I'm just going to leave it running there in the bottom corner. Okay. Starting with our typical shell, and we're going to talk about letting that shell change in height. Okay. So here's a particular example: inner radius 2.5, outer radius 3, and height of 7. And the first thing I want you to do is write an expression for the volume of that cylinder. Don't start yet. Well, I'll talk a little bit, and then I'll go back to attendance. So first, write expression for the volume of that cylinder, and then I'm showing you the volume increasing according to a change in height. So now, what would the change in volume be? So here's going to be one particular volume, and now you're going to express a change in volume. If the height increased by 0.4 meters, starting from 7, and then eventually we're going to get to if the height changed by dH meters, say starting from 7. Make sure you have this, before you start working on changes in volume, you got to have the volume right first. So check with at least a couple students, check with a TA, make sure you have that volume correct before you start trying to write out changes in height, or changes in volume, okay?
I guess you could substitute that for DH just because like that's the change in the height. But I'm not like, for example, if you start out at 7, I'm not sure like, but then again you could just write it as 7 like this, and then do like 7 plus something. That way you could express it. No, this is it's literally just part of the area of the cross section area. That's it.
Okay, I put the volume up there. What do you think? Is that what you put? Is that the volume of that cylinder? Okay, so what would it mean now if I want to find the change in volume if the height increased by 0.4 meters? So now that's a change in volume if the height increases by 4 meters. So how can I represent change in volume? What should I write for change in volume? A symbol. Delta V or dV? Yeah, remember dV is our variable, right? Our variable change. Delta V is when we pick the intervals to start. So this is dV now. This is dV. And so just as a real basic formula for dV, like without looking at this particular problem, if you just in any volume situation, how could you represent dV? dV would be, how would I figure out a change in volume for any volume situation? Okay, so that would be one way to do it if we had constant rate of change. What would another way be to write it?
Final volume minus.
Right, it would be you take your final volume minus your initial volume. Okay, and I'm glad she said MDX because eventually we're gonna take what we find and we're going to see if we can get. In this case, dx would be d what? dH. Okay, so eventually we're gonna be taking our volume expression here and trying to make it look like MDH because if we can make it look like MDH, then we have the rate of change, right? What's the rate of change is m. But for now, we're just starting with final volume minus initial volume, okay? So if the height increased by 0.4 meters, what's the final volume first? I'm going to use this thing, right? But instead of writing this, I'm going to write what? 7.4. So I'm going to have pi times 3 squared times 7.4 minus pi times. And is that the answer? Is that dV? What is that? That's only V final, right? That's only V final because that's a volume, right? So then I'm going to go minus V initial, which is?
Which is pi times 3 squared times 7.
What is it?
Pi times 3 squared times 7.
That's it?
Not that's not all. You have to also do pi times 2.5 squared times 7.
Right, it's this, right? So our starting volume would be this whole thing. All right, we'll stop right there. So there's no reason to that would be a representation of the change in volume if the height changed from 7 to 7.4, or a change of h of 0.4. Everyone good on that? So let's just use that structure right there. And now I'm going to do it for dH. Instead of for 0.4, let's just do it generically for dH. Okay, so here we go. dV equals pi times 3 squared times what?
7.
He wants 7 plus dH. That's right. That'll be the final volume, or sorry, that'll be the final height after it's changed by h. Minus pi times 7 plus dH again. So now that's our final volume. So far I've written the final volume if the height increases from 7 and then increases by dH. So then your final height is 7 plus dH. Does it make sense? Minus what?
Same thing.
Same thing. Starting is the same. So now, why are we doing this? Because what we're doing is, if we can get this thing, like I said, now we want to get this thing right here to look like, if we can get it to look like dV equals something times dH, if I can get this whole expression to look like something times dH, then what did I just figure out? The rate of change of volume with respect to height, right? It's that multiplier on any change in height that will give me the change in volume. So that's what I want. So that's the question, the answer to question number 2. What is the rate of change of cylinder volume with respect to cylinder height? Well, it's what we would get right here if we could transform this thing into something times dH. So it's not too bad. So if we're going to first start by distributing these, right? So I'm going to take the pi times 3 squared and the pi times 2.5 squared and distribute them and multiply by 7 and DH, and then also 7 and DH. And then notice what we have here. So let's green. When I do that first part of the distribution, pi times 3 squared times 7, what do you notice? See that anywhere else?
Oh yeah, the second part.
And notice here it's minus. So what happens? Those two things that I put green boxes around go away. I'm feeling colorful today. How about violet? Okay, and then same thing here. Pi times pi times 2.5 squared times 7. What do you notice? Here it's minus, but here it's minus a minus, which is plus. Therefore, that goes away. So do you see it? So I'm going to distribute, and when I distribute it to the 7, I get plus pi 3 squared times 7, which goes away with the minus pi 3 squared times 7. When I distribute this to the times 7, it will go away and be equal and opposite to that. So I'm left with, back to red, what am I left with? Pi 3 squared times dh. See that? What? Minus pi times 2.5 squared times, and everything else went away. Did you follow it? So look, we're really close now. So dv equals, what do we want to do? We want to write it as something times dh. Do we have the something? Can we do it? What's the something? Pi times 3 squared minus pi times 2.5 squared. So what's the rate of change of cylinder volume with respect to cylinder height? dv equals rate times dh, right? So this rate of change is this thing right here. Here's the rate of change. Okay, so what do you notice about that? What is that an expression for? Pi times 3 squared minus pi times 2.5 squared. Kenny knows. Anyone else notice what that is? Yeah. And it's okay, so then that's the area of what then? If you're looking at, say, this cylinder, what is that the area of? If it's the area of the outer circle minus the area of the inner circle, then you're getting the area of? Yeah, like see this yellow ring. See that? So that the rate of change is the area of the base. That's the area of the base of our right cylinder. So what do you notice about the rate of change? It's the area of the base of the right cylinder. Okay, how does that relate? How does that relate to, go back to page 1 and look at situation 2, where you had the changing rate function? It's a huge takeaway here. How is this conclusion that the rate of change is the area of the base of that yellow circle? Very analogous to, in the area situation, that the rate of change is the function value. See, talk to the person next to you. How are these two situations totally parallel? What's the commonality to both these situations, these rate of change? Go, see if you can come up with it.
I just spent. No, I couldn't major in art, so here I am.
Oh, there you go.
Can I erase what I wrote? Can I erase what I wrote? Anybody? It's on the video. It'll be on the video.
For any change, we also are multiplying that by.
Okay. Who had a revelation? Who thinks, what's the parallel? Tell me your name again. Q.
It relates to the rectangle because it's the same uniform shape at its core, like at its base, but you just change one variable. So that's why the rate of change is the same as just the formula for trying to find the base, the area of the base.
Okay. All right. You're on the right track. Any other? Yeah. Uh-huh. Let's make it yellow. So just like this yellow area, we're really looking at what, like this yellow strip right here, right? So how is this region growing? Where is it growing? How is this area increase? Where does the region grow? Here, right? So there's like this leading edge, right? This leading edge. And what is the rate of change of area? It's like the size of that leading edge, right? If you increase the area a little bit, you're going to get that much more area. So the leading edge of how this thing is growing gives us the rate of change. How is this growing? How's the volume of the cylinder growing? Up. Where's it growing? In height, at the top, right? The leading edge is the top. And how much does it grow by if it goes up a little bit? The amount of the size of the leading edge. Do you see that? So the area is growing right to left. It grows by the amount of, say, a yellow strip. That's the size of the leading edge of the quantity that's increasing. This volume of the cylinder, it's growing up. How much? What is its rate? It grows a little bit by the size of the leading edge, which is the area of that ring.